Okay, so in general, we have, in general, when we try to solve some problem, we have some neural network, which is parameterized by parameters, theta parameters. We have some cost function. We have SGD or some modification of SGD, and we need to minimize the cost function, and thanks to it, we solve some problem. And in general, here everything is completely solved. Yeah, we know how to construct our function, we know how to construct cost function, our neural network, how to choose, how to minimize. This is completely solved. We only need to pay some money for people who train the model. But we can think about optimizations in different way, because you know SGD is not only one possible kind of solving the minimization problem. And one of the other approaches is hypernetworks. Who know what is hypernetworks? Yeah, almost the same number. Yeah. So hypernetworks is the paradigm that uses two neural networks. But the first neural network, we will call it the hypernetwork, has trainable parameters. And the network produces weights to the another network, which we call the target network, which is not trained by gradient descent because the weights are directly produced by the hypernetwork. And you know, here I want to visualize, for example, you want to construct some classifier. So to the target network goes elements which we want to classify, cat or dogs. And we have hypernetwork which produces the weights to our target model. So the concept is quite nice. The hypernetwork weights are trained classically by SGD or some modification. And the parameters of the network are directly produced by the hypernetwork. And you know, it is quite similar to the classical optimization. But you know, when we optimize something by the gradient descent, we change the weights of the network only in small steps. We have a lot of data and produce a lot of small steps. And here, when you change the hypernetwork weights a little bit, you can change the weight of target network completely. Yeah, because you know, we have a lot of layers and neurons or whatever we have here. So when we optimize the parameters of the gradient descent, the parameters of the target network can change completely. And you know, this paradigm can be used in many different approaches. I love hypernetworks. People who knows me know that I have a lot of projects where I use hypernetworks. Today I say about the project with point cloud and NeRFs, but in general it can be using continual learning, generative model, feature learning, and etc. So if you want to construct a project with hypernetworks, you can contact me. I always do some project with hypernetworks. Okay, how hypernetworks can be combined with the NeRF or point cloud? I need to say something few words about ENRs. Who know what is ENR? Okay, so ENR is something like that we have neural networks which we want to use to encode some discrete data. For example, when we have the image, we can train the model to encode structure of the image in the neural weight. It's completely simple. We train the model that to the network we put the xy coordinates, so the coordinates of the pixel. Of course, in training data set, we have only the integer numbers, the rows and the weight and the parameters of the pixel. And the neural network takes the coordinates and produces the RGB color. And you encode everything in the neural network weights. Was for usually to compress our image or for hyper resolution, because you can run your code not only in existing pixel, but I don't know, in the middle places. Yeah. So ENRs produce continual representation of the discrete data. Okay, and the second concept which I want to say about is the point clouds. Yeah, and here we have autoencoder. I know that all people use the diffusion models, but I don't know, few years ago, autoencoders rules. So to the encoder goes the point cloud. Point cloud has some structure because they are invariant to permutation, because you know you can put the point cloud in any order. Then goes to the latent space and produce the output. And usually you need two fixed the input size and the output size, yeah? And this is a problem for point clouds, because point clouds, when you have a complicated point cloud, you need a lot of points. If you have a simple point cloud, only a few points is enough. So it is a bottleneck of this model. And on the input, it is possible to solve by point nets. This is a classical model which uses some kinds of attention. But on the output, we have a problem because we need a fixed number of points. So to solve this problem, we can use these two concepts which I talked about, so the hypernetworks and ENRs. So we changed the classical autoencoder at the output. So the decoder not produce the point directly, but produce the weight to the target network. And the target network transfer 3D coordinates XYZ to 3D coordinate XYZ. In general, we take the point from uniform distribution of the ball and transfer it to the in the surface of the object. And we train it with some reconstruction function. And you know, when you want to reconstruct this car, you reconstruct it point by point. So when you need 2,000 points, you need to run this code 2,000 of times, yeah? And you can train this model with the fixed number of points, but in inference time, you can run the target network as many times as you need. And this concept is also nice because we can use the target network with nice trick, yeah? So in general, if all points from the ball goes to the surface of the object, so if you take the mesh of the ball, so something which covers all points, and transfer by the target network, you obtain mesh. And this is quite nice because usually when you want to train on the point cloud, you need point cloud. When you want to train on the mesh, you need mesh. And here we train on the point cloud, and in inference time, we obtain the mesh. And you know, thanks to this, we can produce a model which produces meshes by using only point clouds. Of course, we can produce some elements, we can make some interpolation, and we can do everything what we can do with the generative models. This paper is nice because it was published on ICML, and the concept is quite nice to produce the network instead of the discrete data. The next level of our solution is to use something more, it's flow. Who knows what is flow? Continual normalizing flow. Okay, nice. So you know what is GAN. GAN is that you have the discriminator and generator, and they fight each other to produce them. You know what is autoencoder, yeah? So flow is a autoencoder, but the decoder is the reverse function of the encoder. So in practice, you produce the network which don't have any bottleneck. It goes from the same dimension to the same dimension. And you can back to the input data. And such models are nice. One of the most important models is quite old, but is a Fjord, which use this transformation by differential equation. Yeah, in general, you have the dynamic function, and this dynamic function is integrated from the Gaussian distribution to the distribution of data. And this integration is reverse. So you can go from the Gaussian distribution to the distribution of data, and you can back to the Gaussian data. Why I say about it? Because we also use it in the target network, yeah? Because target network can be any possible network, so we can use also flow models, so CNFs. And you know, it's nice because you can transfer the distribution of data, the data to the data from uniform sphere to the data of the manifold with continuous and reversing the distribution, so these objects are homomorphic in general. So the idea is that all point clouds are empty inside, yeah? Because when you take the camera and produce some some 3D reconstruction. You take the points only from the surface of the object. You don't have any point inside. Yeah. So your model should reflect these properties. So we use some distribution. We called it a log normal distribution, and this log normal distribution is a distribution which use Gaussian on the sphere. And when you produce the large sigma, so this distribution is quite big, and when you use small distribution, it is quite tiny. So you can model the sphere inside the sphere and the point of the sphere. So in practice here, we don't have the uniform distribution on the ball, but on the sphere. And we train it with large sigma because we need log-logical function, because log-logical function needs the correct distribution. And then we goes to the very tiny representation. And thanks to it, we obtain the transformation, which is quite nice. Yeah, when you produce the object from the noise, if you do it from something which is not correctly homogenical correctly, so here we don't have any holes, and here we have one hole. These points are messy. So the elements from the centers go to the front of the plane and to the end of the plane. And when you have something that is empty inside and your transformation is smooth, you can see that it is a smooth transformation from the sphere to the plane. Like you only take these parts and like modeling in hands, something like that. And thanks to it, we obtain the better fitting of the object. And it was okay. It works okay. So we try to generalize to the real object. So when you scan some object, for example, here, some parts are scanned partially, because you don't have enough time to go around each element of the scan. So you have only the part of the element. So we decide to produce some project, some model, which is able to generate the missing parts. But sometimes it's not obvious what exactly is here. So we try to generate in many different scenarios. So when we want to produce fill the empty space with many possible alternatives, and thanks to it, when you have the half of the elements, your model is able to produce the missing part. Of course, when you change the sedan to the hatchback or something like that, you have to a little bit change the existing parts to be correctly fitted, but the model should do it. And thanks to it, we are able to produce the missing part of the elements. But sometimes it's problematic because the legs can be too long or too short. And it's a problem because this model don't have any knowledge about the environment. So we add some module which takes some constraints. The floor constraint is quite easy because we say that the floor is on the level 0 and that's all. And we optimize it in this way that the model can correctly change the legs to be consistent with the environment. How the model looks like, we have the same autoencoder as before, but we have two encoders. To the first encoders go the existing parts. So here we don't have any probabilistic distribution. Here we have the second encoder. Here is the Gaussian distribution, like in the VAR or something like that, generative model. They are concatenated, and we produce the hypernetwork, which produce the target network. And these two representations are completely different, but because one target network produces the final object, it works in this sense that it is correctly stitched. And here is the example that here goes the first part and here the second part from different objects. So when we mix different kinds of cars, the model can produce some correct stitches of these elements. Of course, when we have only one part, here goes the existing parts, and to the next encoder goes the Gaussian noise, and we can produce the missing part. Of course, this is also the problem with colors, and a lot of people is able to produce by point clouds and meshes and point clouds, but it is a problem with colors. So we decided to add colors to the IROS model, and this is a small modification. The first part you already know because I say about it. Here goes the point cloud without colors, produce the latent, and the target network recover the shape. And we add the second autoencoder. Here goes the point cloud with colors, because this model is already trained, and we train the second part. The network is learn only the colors because the shape is already trained. And thanks to it, we obtain the second target network. And you know, it goes that points goes here, then goes to the plane, then from the planes goes to the color plane, and we obtain the correctly color point cloud. Yeah, of course we need the meshes, and we can use the same trick as before. We transfer the uniform sphere by target network, and after that by the second target network, then we obtain the mesh with colors. And you know, it's quite nice. And a few years ago, it was a SOTA solution. Yeah, we are able to produce this kind of object. But everything was changed when the NeRF was invited. Yeah, it was constructed. Yeah, who know what is NeRF? I hope that people who was yesterday on my first talk know what is NeRF. Yeah, but in general, NeRF works in this way that we put the images to our model. First, we estimate the position of the camera, and then we produce the neural network, which is able to produce the 3D object. And NeRF is a classical neural network which takes XYZ position in 3D space and camera position. And in general, this is trained in this way that we have the 2D images, we have the position of the camera, ray goes to the image and in the space. Then we sample the point from the ray, and we train neural network in such a way that we take the point, the position camera, and produce the color RGB and transparent of the point. And we average these numbers, and the average of this number should reconstruct this point here. So we train it with the reconstruction function, this classical mean square error. And in inference time, when we have the new position and we want to produce the image, we first have the white card, and we produce the ray through each pixel of the scene. Then the ray goes through the 3D scene. We sample point here. In the inference time, we run the model which produced the RGB color sigma. We aggregate it, and the aggregate value goes to the color of the pixel. Because we trained the model in such a way that the average of this number reproduce the color here. So in inference, it works in the same way. Rays are close to each other, and thanks to it, the network produces the consistent representation of the object. In practice, we have only the neural network. And you know, this solution is nice because it fits for hypernetworks, yeah, because we can produce NeRF by hypernetworks. So the first idea to use the hypernetworks in NeRF is to point to NeRF model. So we have the point cloud with colors, and we want to transfer it to the correct NeRF, yeah. And you know, it works that you put the point cloud with colors, and on the output of the model you obtain the neural networks, the NeRF, which produce each possible renders. Yeah? The model is quite easy. To the autoencoder goes the point cloud, and at the output we obtain the NeRF, which transfer the 3D coordinates XYZ and position of the camera to the color transparency, and thanks to it we can produce easy transformation. It works quite nice, and we can convert point clouds to them. But the problem is that the quality of these renders are not enough. So we decide that there exists some problem in the model. So we think that the problem is that is autoencoder not GAN. Yeah, I know that you think that diffusion model should solve everything, but here we have GANs. GANs are nice because we do not need any camera position, and we can use only one renders per object, yeah, because it works that we sample point, throw to the generator, produce the NeRF, produce randomly chosen position, reconstruct some novel view, and this one novel view goes to the discriminator, and some elements from the training data goes to the discriminator. And we can train in such a way that our generator produces the NeRF. And it occurs that it works nice. You know, this car looks like a real car. We have transparent glasses, and everything is quite okay. In practice, we obtain a nice render. So substituting classical meshes with NeRFs solve the problem with a generative model. What we also can do by NeRF, we can also combine it with the meshes. Yeah. So here we want to produce avatars of the people, and you know there exists a lot of models which generate meshes. Yeah. So here we generate a mesh, and we want to train our Gaussian our NeRF. So we combine it with the mesh in such a way that NeRF can work only some shell of the mesh. So when we are close to the mesh, you can produce color and opacity, but when we are far from the mesh, we force it to give zeros. And thanks to it, the NeRF is connected with the mesh. And thanks to it, we can train our model on the single phase, and after that, we can move the mesh to obtain novel position of the phase. Okay, so. The next model which I can say about is a multiplane NeRF. Multiplane NeRF is a new approach to the NeRFs. The classical NeRFs transfer position to RGB color transparency. There exists voxel NeRF, which use not only the point, but some points which are close to the point we want to predict. We can also use three-plane model. It works that we train 3 planes posed in this position, usually by some generative model dedicated for images, and we can aggregate the projection of the point to this plane and produce color and opacity. And finally, we have our solution, multiplane. Multiplane use the same idea, but we not train the planes, but we use this plane which exists in dataset. Yeah, because in NeRF, you know, we have some existing elements, and we aggregate information from it. How can be used? You know, when you have existing images, and you need to construct the function which take the 3D point clouds, predict RGB current sigma. You use small neural network, but you use on the input not only the position, but also the position of the point which goes from the perspective projection on the existing images. Thanks to it, we can aggregate information from the existing elements, and the network is. How can we use it? Because you know NeRFs are quite slow. So you know we can train NeRF for 3,000 epoch, and we obtain some PSNR. And our solution, which is multiplane, in one step, in one shot, produce the PSNR with this level. Yeah. So of course it's not perfectly done, but you know we need to use only one element. How the model work? It uses hypernetworks. I know that this picture is quite complicated, but here we have the multiplane, and here exists we have existing elements. And yeah, I know it's quite complicated, but in practice, we take the existing images, they go to the hypernetwork. Hypernetwork produce the weights. The weights are connected with the weights of universal NeRF, and they reconstruct the novel view. And thanks to it, hypernetwork takes the existing images and produce weights to the target network. The image is a little bit complicated, but the application is easy. And thanks to it, we are able to reconstruct some object in one step. So we take the images and hypernetwork in one step produce them. Okay, so this is all, but you know who was on my previous talk, you know that at the end of all my talks, I present some projects which you can be a part. So if you are interested in doing the NeRF project, you can go to our page, find me, and we can work. Here I won't say that The nice idea is to combine NeRF and Gaussian splatting. We already started some project. There exists NeRF which aggregate information with Gaussians to produce the opacity and color. They are taken from the center of Gaussian. And we have the project to substitute this part by Gaussian splatting model, which I talked about last time. So if you are interested in this project, we're looking for new people. Thanks a lot.